In this video, I will show how to use depth-dependent calculations. It's important to know that depth-dependent calculation does not require to have the data loaded or fits. However, it's better to do depth-dependent calculation based on the parameters obtained from the fit of the experimental data. For example, in this case, I copy my parameters from the obtained from the fit, my electron phonon coupling strength and my electron thermalization time. Then I have to make sure that my fluence is the same as in my usual fit and my temperature is the same as my usual fit. It's the most natural way to do it. And in this way, I know that my fit works, I know that my heat capacity is correct, and my other parameters are already correct and already saved because I used the fit option. Again, when the fit all button clicked, all these parameters, they will be saved. So if I close program and then I reopen, then they will be the same. And here I need to choose the modeling time. It always starts from -1 picosecond. And for example, here I go from -1 to 4. Usually you don't have to go that far because after 2 something picosecond, usually you already have equilibrium between temperatures. However, it does not hurt to make more. Then the steps, I recommend to have few thousand. If you don't have enough steps, your model can break because you use Runge-Kutta methodology. Here, steps are required. In the experiment, your steps are defined by number of experimental points. And then I can click, for example, depth-dependent, and it calculates and saves simultaneously. It should be relatively fast. However, if the save time can take some time, and save files time can take some time. And as you can see here, all the files, this is my initial file, and here by the timestamp you can see that these all files that I got saved. So I got model that lattice, electrons, pulse power, and stress, electron lattice stress. Let's open any of those files. For example, here let's go for temperature lattice. As you can see, one of them with long names, with some these additional parameters, another one without. That with long name is additional code for Igor Pro, and in the Igor Pro video you can check what it means. I will open without it, so to have X for origin or for other programs. And as you can see, I have my file, the first column is my X, and then I have nanometers, and then as you can see, the last one is 78, not 80, 78. The first one is 0. It's on the you can see that this is my temperatures, basically the highest on the surface, and then lower and lower as much as I go inside of the sample. My recommendation to using it to, if I go for 41, for example, I want to increase the sample thickness a little bit to have the last layer exactly at 80, because in this way I calculate only on one side of each layer, but then I will calculate on another side. It does not affect the overall this model too much, because I calculate for each layer individually. I do not use the entire thickness, unlike the regular not depth-dependent model. Then you can use compare option 2, and let's go and let's see. So you can see that for compare option you will have much more files, because you have not just the depth-dependent, but you also have files with the name of simple, additionally, and then you have separately TTM simple that it will just basically resave the simple model. So you have simple models that use for fits. For this model, when you assume that the temperature is the same, you have depth-dependent model that you can make separately for each layer. Realistically, from the experience, the average over those Of course, it depends on the sample thickness and the penetration depth. It's in good agreement, even up to case when your penetration depth is 3 to 4 times less than your sample thickness. You still have good agreement. If your difference is more, then your accuracy of the modeling decreases.